So now the relationship that we can show between uniform circular motion and simple harmonic motion is as follows. A mass sitting on the edge of a rotating turntable can be represented by these two things. And a two-dimensional motion, which is what's represented, and the x and y position of the object at any time can be found by applying these equations. And to find angular velocity, which is going to be constant, is represented by this equation. And these are the equations now for calculating displacement, velocity, and acceleration for systems experiencing simple harmonic motion. This first equation is about displacement. Now going more in depth with the displacement equation, it is the amplitude is simply the maximum displacement from the object at its equilibrium point. So in other words, the same equation applies to the position of the object experiencing simple harmonic motion and to the one experiencing one-dimensional from the position of uniform circular motion. So these two equations are related. The second equation is for velocity. And this third equation is about acceleration. The velocity equation, in a simple harmonic motion, velocity constantly changes, oscillating just as the displacement does. So when the displacement is at its maximum, however, the velocity is zero, and when displacement is at zero, the velocity is at its maximum because they are inversely related. Also, for the acceleration equation, acceleration oscillates in simple harmonic motion. So if you consider a spring with a mass, when the displacement is zero, the acceleration also is zero because no force is applied. And when displacement is at its maximum, acceleration will be at its maximum because the spring applies a maximum force. And the force being applied in the spring is in the opposite direction of the displacement. So this is my example now. My spring constant is going to be 15 newtons per meter, and I'm going to have a 45-gram ball. So first you need to convert the 45-gram ball into kilograms, which would be 0.045 kilograms, and then you take the angular velocity equation to find a W to fill in for all of these values. So then you're left with 18s to the negative 1 for your W value. And an additional fact for this problem, you're going to be pulling the ball 10 centimeters high before you're dropping it, ultimately relating that A is equal to 10 centimeters. So my first equation is written like this. X for the displacement is equal to 0.10 meters times sine, within brackets, 18s to the negative 1 times t. My second equation for velocity is 0.10 meters times 18s to the negative 1 times sine, in brackets, 18s to the negative 1 times t. And my last equation is A equals negative 0.10 meters times 18s to the negative 1 squared times cosine, in brackets, 18s to the negative 1 times t.